Azure Load Balancer. What is load balancing? A load balancer is a device that distributes network or application traffic across a cluster of servers. Load balancing improves responsiveness and increases availability of applications. A load balancer sits between the client and the server farm, accepting incoming network and application traffic and distributes the traffic across multiple backend servers using various methods. By balancing application requests across multiple servers, a load balancer reduces individual server load and prevents any one application server from becoming a single point of failure, thus improving overall application availability and responsiveness. Load balancing is the most straightforward method of scaling out an application server infrastructure. As application demand increases, new servers can easily be added to the resource pool, and the load balancer will immediately begin sending traffic to the new server. Core load balancing capabilities include either Layer 4, Layer 7, or the GSLB. Layer 4 or L4 load balancing is the ability to direct traffic based on data from network and transport layer protocols such as IP address and TCP ports. Layer 7 or L7 load balancing and content switching is the ability to make routing decisions based on application layer data and attributes such as HTTP header, Uniform Resource Identifier, SSL Session ID, or HTML form data. And finally, Global Server Load Balancing or GSLB extends the core Level 4 and Level 7 capabilities so that they are applicable across geographically distributed server farms. With Azure Load Balancer, you can scale your applications and create high availability for your services. Load Balancer supports inbound and outbound scenarios, provides low latency and high throughput, and scales up to millions of flows for all TCP and UDP applications. Load Balancer also distributes new inbound flows that arrive on the load balancer's front end to the backend pool instances, and it is related to rules and health probes available to that load balancer. Additionally, a public load balancer can provide outbound connections for virtual machines inside your virtual network by translating their private IP addresses to public IP addresses. Azure Load Balancer is available in two SKUs, Basic and Standards. There are differences in scale, features, and pricing. Any scenario that's possible with Basic Load Balancer can also be created with a Standard Load Balancer, although the approaches might differ slightly. As you learn about Load Balancer, it is important to familiarize yourself with the fundamentals and SKU specific differences that are available. You can use Azure Load Balancer to load balance incoming internet traffic to your VMs. This configuration is known as Public Load Balancer. You can also use Azure Load Balancer to load balance traffic across VMs inside a virtual network. You can also reach a load balancer front end from an on-premises network in a hybrid scenario. Both scenarios use a configuration that is known as internal load balancer. You can use load balancer in Azure to port forward traffic to a specific port and specific VMs with inbound network address translation or NAT rules. You also can provide outbound connectivity for VMs inside your virtual network by using a public load balancer. A very important matter to note is that you can custom tailor your load balancer. Azure provides a suite of fully managed load balancing solutions for your scenarios. If you're looking for transport layer security or TLS protocol termination, or SSL offload, or per HTTP HTTPS request, application layer processing, then review the application gateway part of Microsoft Azure documentation. If you're looking for global DNS load balancing, you should review the traffic manager option of the load balancers in Azure documentation. Your end-to-end scenarios might benefit from combining these solutions as needed. A load balancer resource can exist as either a public load balancer or an internal load balancer. The load balancer's resources function are expressed as front end, a rule, a health probe, and a backend pool definition. You place VMs into the backend pool by specifying the backend pool from VM. Load balancer resources are subjects within which you can express how Azure should program its multi-tenant infrastructure to achieve the scenario that you want to create. There is no direct relationship between load balancer resources and actual infrastructure. Creating a load balancer doesn't create an instance, and capacity is always available to create another one. So it is very important for you to distinguish between the load balancer as an object in comparison with the real object of an object-oriented programming concept. In this case, since the real instance does not create at all, you always have capacity to create another one. Let's talk about some fundamental features of a load balancer. Load balancer provides the following fundamental capabilities for TCP and UDP applications. Remember, in this case, you're talking about an L4 load balancer. Those features are load balancing, port forwarding, application agnostic and transparent, automatic reconfiguration, health probes, and outbound connections of SNATs. Within the following slides in this video, we will go deeper into each one of these features. So let's start with the load balancing. With Azure Load Balancer, you can create a load balancing rule to distribute traffic that arrives at front-end to back-end pool instances. Load Balancer uses a hash-based algorithm for distributing inbound flows and rewrites the headers of flows to backend pool instances accordingly. A server is available to receive new flows when a health probe indicates a healthy backend point. By default, Load Balancer uses a 5-tuple hash composed of source IP address, source port, destination address, destination port, and IP protocol number to map flows to available servers. You can choose to create affinity to a specific source IP address by opting into a 2 or 3-tuple hash for a given role. All packets of the same packet flow arrive on the same instance behind the load balanced frontend. When the client initiates a new flow from the same source IP, the source port changes. As a result, the 5-tuple might cause the traffic to go to a different backend point. The other feature is port forwarding. With Load Balancer, you can create an inbound network address translation role to port forward traffic from a specific port of a specific front-end IP address to a specific port of a specific backend instance inside the virtual network. This is also accomplished by the same hash-based distribution as load balancing. Common scenarios for this capability are Remote Desktop Protocol, or RDP, or secure shell SSH sessions to individual VM instances inside the Azure Virtual Network. You can map multiple internal endpoints to the various ports on the same front-end IP address. You can use the front-end IP addresses to remotely administer your VMs over the internet without the need for an additional jump box. Next feature that we're going to look at is the application agnostic and transparent. Load balancer does not directly interact with TCP or UDP or the application layer, and any TCP or UDP application scenario can be supported. Load balancer does not terminate or originate flows, interact with payload of the flow, and provides no application layer gateway function, and protocol handshakes always occur directly between the client and the backend pool instance. A response to an inbound flow is always response from a virtual machine. This is important to understand that the load balancer itself does not provide any response. When the flow arrives on the virtual machine, the original source IP address is also preserved. A couple of examples to further illustrate transparency are: every endpoint is only answered by a VM. For example, a TCP handshake always occurs between the client and the selected backend VM. A response to a request to a front end is a response generated by backend VM. When you successfully validate connectivity to a front end, you are validating the end-to-end connectivity to at least one backend virtual machine. Other example, application payloads are transparent to load balancer, and any UDP or TCP application can be supported. For workloads which require per HTTP request processing or manipulation of application layer payloads, for example, parsing of HTTP URLs, you should use a layer 7 load balancer like application gateway. Because load balancer is agnostic to TCP payloads, TLS offloads SSL is not provided. You can build end-to-end encrypted scenarios using load balancer and gain large-scale out for TLS applications by terminating the TLS connection on the VM itself. For example, your TLS session keying capacity is only limited by the type and number of VMs you add to the backend pool. If you require SSL offloading, application layer treatment, or wish to delegate certificate management to Azure, you should use Azure's Layer 7 load balancer application gateway instead. The other feature that we're going to go through is automatic reconfiguration. Load balancer instantly reconfigures itself when you scale instances up or down. Adding or removing VMs from the backend pool reconfigures the load balancer without additional operations on the load balancer resource. And then health probes. To determine the health of instances in the backend pool, load balancer uses health probes that you define. When a probe fails to respond, the load balancer stops sending new connections to the unhealthy instances. Existing connections are not affected, and they continue until the application terminates the flow. An idle timeout occurs, or the VM is shut down. Load balancer provides different health probe types for TCP, HTTP, and HTTPS endpoints. Additionally, when using classic cloud services, an additional type is a load, which is the guest agent. This should be considered to be a health probe of last resort and is not recommended when other options are available. Another feature is regarding outbound connections. All outbound flows from private IP addresses inside your virtual network to public IP addresses on the internet can be translated to a front-end IP address of the load balancer. When a public front end is tied to backend VM by way of load balancing rule, Azure programs outbound connections to be automatically translated to public IP address in the front end that enable easy upgrade and disaster recovery of services because the front end can be dynamically mapped to another instance of the service. Also provides easier access control list management. ACLs expressed in terms of front-end IPs do not change as services scale up or down or get redeployed. Translating outbound connections to a smaller number of IP addresses than machines can reduce the burden of whistle listing. For more information regarding this, Azure has extensive documentation on outbound connections. Standard Load Balancer has additional SKU-specific capabilities beyond these fundamental capabilities that we talked about so far. Let's take a look at Load Balancer SKU comparison. Load Balancer supports both basic and standard SKUs, each differing in scenario scale, features, and pricing. Any scenario that's possible with basic load balancer can be created with a standard load balancer as well. In fact, the APIs for both SKUs are similar and invoked through the specification of SKU. The API for supporting SKUs for load balancer and the public IP is available starting with the 2017-08-01 API. Both SKUs have the same general API and a structure. However, depending on which SKU you choose, the complete scenario configuration might differ slightly. Load balancer documentation calls out when an article applies only to a specific SKU. To compare and understand differences, you better reference to the following table that I'm going to present in the coming slides. For more information, you can also go to the Azure documentation and look at the standard load balancer review of the Azure documentation. Note that new designs should adopt standard load balancer. Standalone VMs, availability sets, and virtual machine scale sets can be connected to only one SKU, never both. When you use them with public IP addresses, both load balancer and the public IP address SKU must match. Load balancer and public IP SKUs are not mutable. It is a best practice to specify SKUs explicitly, even though it is not yet mandatory. At this time, required changes are being kept to a minimum. If the SKU is not specified, it is interpreted as an intention to use the 2017-08-01 API version of the basic SKU. Now let's talk about a very important matter. Standard Load Balancer is a new load balancer product and largely a superset of basic load balancer. There are important and deliberate differences between the two products. Any end-to-end scenario that's possible with basic load balancer can also be created with a standard load balancer. If you are already used to basic load balancer, you should familiarize yourself with a standard load balancer to understand the latest changes in behavior between a standard and basic and their impacts. Let's take a look at the differences through comparison. So the first thing that really matters is the backend pool size. As you can see, the standard SKU supports up to 1,000 instances, while the basic SKUs support up to 100 instances. So the comparison here is 10 times more support when it comes to the standard. Looking at the backend pool endpoints, any virtual machine in a single virtual network, including blend of virtual machines, availability sets, virtual machine scale sets, and so can use the standard. While when it comes to the basic, virtual machines in a single availability set or virtual machines scale set are the options. The health probes are basically what are coming next. And with the standard, you can do TCP, HTTP, and HTTPS, while with the basic, you can only do TCP and HTTP. Lack of secure HTTP in the basic is another decision-making factor to move you more towards the standard. So health probe down behavior. When it comes to that, with the standard, TCP connections stay alive on instance probe down and on all probes down. While with the basic, TCP connections stay alive on instance probes down, all TCP connections terminate on all probes that are down. Which, as you can see, it's a little bit different, and again, it moves you back towards the standard. When it comes to the availability zones, look at the options you get with the standard. Azure Monitor, multidimensional metrics include bytes and packets counter, health probe status, connection attempts, TCP syncs, outbound connection health, SNAT, successful and failed overs, active data plan measurements. But when it comes to the basic, you get Azure-like analytics for public load balancer only. SNAT exhaustion alerts, back and pool health counts also exist over there. And one of the most beautiful differences between standard and basic is the pricing, where the basic is free, no charge, but on the standard, you're getting charged based on the number of rules, data processed inbound and outbound associated with resources. HA ports, when it comes to standard, you're using the internal load balancers, while on the basic, they're not available. Secure by default. So under the standard, you have public IP, public load balancer endpoints, internal load balancer endpoints, which are closed to inbound flows unless whitelisted by a network security group. But when it comes to the basic, it's open by default, and network security groups are optional. For the outbound rules, with the standard, it's declarative outbound NAT configuration using public IP address or public IP prefixes or both. Configurable outbound idle timeout is 4 to 120 minutes, and custom SNAT port allocation happens over there. While the outbound rules are basically unavailable under the basic. TCP reset on idle. So with the standard, enable TCP reset or TCP RST on idle timeout on any rule. And again, this is not available in the basic. Multiple front ends. So you can have inbound and outbound for a standard SKU, while when it comes to the basic, you only can set up the inbound. For the management operations, most operations take less than 30 seconds, while under the basic, typically they take between 60 to 90 plus seconds. For service level agreement, there is no SLA for basic, while you get the 99.99% for data path with 2 healthy virtual machines under the standard. And finally, under the outbound connections, when it's under the basic, you get single front end, select at random when multiple front ends are present, which is not very efficient. And when only internal load balancer is serving a virtual machine availability set or virtual machine scale set, and the default SNAT is used. While when you go to the standard SKUs, You can explicitly define pool-based outbound NAT with outbound rules. You can use multiple front ends with per load balancing rule opt-out. An outbound scenario must be explicitly created for the virtual machine and availability set or virtual machine scale set to use outbound connectivity. Virtual network service endpoints can be reached without defining outbound connectivity and don't count towards data processed, and therefore you're not going to get charged for those. Any public IP addresses, including Azure PaaS service, not available as virtual net service endpoint, must be reached via outbound connectivity and count towards data processed, and you will get charged for it. When only an internal load balancer is serving a virtual machine availability set or virtual machine scale set, outbound connection via default SNAT aren't available, and you have to use outbound rules instead. Outbound SNAT programming is transparent protocol specific based on protocol of the inbound load balancing rule. So, now let's talk a little bit about the concepts that we have gone through so far. The first concept that we mentioned a lot was the public load balancer. A public load balancer maps the public IP address and port number of incoming traffic to the private IP address and port number of the VM, and vice versa for the response traffic from the VM. By applying load balancing rules, you can distribute a specific type of traffic across multiple VMs or services. For example, you can spread the load of web request traffic across multiple web servers. The diagram that you see here in this picture shows a load balanced endpoint for web traffic that is shared among 3 VMs for the public and TCP port 80. These 3 VMs are in a load balanced set. When internet clients send web page requests to the public IP address of a web app on the TCP port 80, Azure Load Balancer distributes the request across the 3 VMs in the load balance set. For more information about load balancer algorithm, you can use the documentation of Microsoft under load balancer features sections. By default, Azure Load Balancer distributes network traffic equally among multiple VM instances. However, you can also configure sessions affinity and change it to however you want it to be balanced. Next concept we want to talk about is the internal load balancer. An internal load balancer directs traffic only to resources that are inside a virtual network or that use a VPN to access Azure infrastructure. In this respect, an internal load balancer differs from public load balancer. Azure infrastructure restricts access to the load balanced front-end IP addresses of a virtual network. Front-end IP addresses and virtual networks are never directly exposed to an internet endpoint. Internal line of business application run in Azure and are accessed from within Azure or from on-premises resources. An internal load balancer enables the following type of load balancing. Within a virtual network, load balancing from VMs in virtual network to a set of VMs that reside within the same virtual network. For a cross-premises virtual network, load balancing from on-premises computers to a set of VMs that reside within the same virtual network. For multi-tier applications, load balancing for internet-facing multi-tier applications where the back-end tiers are not internet-facing. The back-end tiers require traffic load balancing from the internet-facing tier. For line of business application, load balancing for line of business application that are hosted in the Azure without additional load balancer hardware or software. The scenario includes on-premises servers that are in the set of computers whose traffic is load balanced. Let's take a look back again at the figure over here and review what we get. So we get within virtual network, we get for cross-premises virtual network, for multi-tier applications, and for line of business applications. Okay, so one of the subjects that everyone who uses cloud is concerned about is the pricing. Let's look at how the load balancing pricing works. Standard load balancer usage is charged based on number of configured load balancing and outbound rules. Inbound NAT rules do not count against the total number of rules. Also based on amount of data processed inbound and outbound irrespective of rule. For standard load balancer pricing information, you can go to the load balancer pricing page of the Microsoft Azure. And what is amazing is basic load balancer is offered at no charge. So if you can live with the lack of features that the basic load balancer has, then you can simply go ahead and use that instead. Also, different SLAs are available for the standard, and for information about the standard load balancers, you can go to the Azure documentation. Of course, like any other service, there are some limitations coming with load balancers. Let's go through those together. Load balancer is a TCP or UDP product for load balancing and port forwarding for these specific IP protocols. Load balancing rules and inbound NAT rules are supported for TCP and UDP and not supported for other IP protocols. So again, they only support TCP and UDP protocols. Other IP protocols such as ICMP are not supported at all. Load balancer does not terminate, respond, or otherwise interact with the payload of a UDP or TCP flow. It is not a proxy. Successful validation of connectivity to a front end must take place in band with the same protocol used in the load balancing or inbound NAT, TCP or UDP rule, and at least one of your virtual machines must generate a response for a client to see a response from a front end. Not receiving an in-band response from the load balancer front end indicates no virtual machines were able to respond. It is not possible to interact with a load balancer front end without a virtual machine able to respond. This also applies to outbound connections where the port masquerades SNAT is only supported for TCP and UDP. Any other IP protocol, as we said, including ICMP, will also fail. So assign an instance level public IP address to mitigate such problems. The other matter is, unlike public balancers which provide outbound connections when transitioning from private IP address inside the virtual network to public IP addresses, internal load balancers do not translate outbound originated connections to the front end of an internal load balancer, as both are in private IP address space. This provides potential for SNAT port exhaustion inside unique internal IP address space where translation is not required. The side effect is that if an outbound flow from a VM in a backend pool attempts a flow to front end of the internal load balancer in which pool is residing and is mapped back to itself, both legs of the flow don't match and the flow will fail. If the flow did not map back to the same VM and the backend pool which created the flow to the front end, the flow will succeed. When the flow maps back to itself, the outbound flow appears to originate from the VM to the front end, and the corresponding inbound flow appears to originate from the VM to itself, from the guest OS's point of view, the inbound and outbound parts of the same flow don't match inside the virtual machine. The TCP stack will not recognize these halves of the same flow as being part of the same flow as the source and destination don't match. When the flow maps to any other VM in the backend pool, the halves of the flow will match and the VM can successfully respond to the flow. The symptom for the scenario is intermittent connection timeouts when the flow returns to the same backend which originated the flow. There are several common workarounds for reliability achieving the scenario, which is originating flows from the backend pool to the backend pool respective internal load balancer front end, which include either insertion of a proxy layer behind the internal load balancer or using DSR style rules to avoid such configuration happening. Customers can combine an internal load balancer with any third-party proxy or substitute any internal gateway in order to avoid any such problem happen. So this is basically most of the things that we wanted to talk about regarding the load balancers, and this concludes the conceptual part of this video.